Today we're going to continue with our combinational logic with decoders first. Now, a decoder is a circuit that takes a binary number as an input and selects a unique output for each binary number that is in each unique binary number that is input into the circuit. So, say you have a 2-digit binary number, and you wish to select one of 4 outputs. So you have Q1 or Q0, Q1, Q2, Q3. Q is often used to indicate an output because an O for an output can be easily confused for the number 0. So you'll often see Q as an output letter. So if your binary number is 0, 0, you'll have a 1 here and zeros across the rest of them. 0, 1, you'll have a 1 in Q1. 1, 0 or 2, you'll have 0, 0, 1, 0. And 3, you'll have 0, 0, 0, 1. So one unique output for each binary number input. The circuit for this is fairly simple. Have each of your inputs inverted, and you'll have AND gates for your outputs. So you have 0, 0 would be Q0 would be an AND gate. It'd be not A and not B. For Q0. For Q1, you want not A and B. Not A and B. For Q2, you want A and not B. And finally, you have A and B for Q3. Okay. This is it. All right. So you have your inputs inverted, so you have access to both inverted and regular inputs, and you feed them into AND gates for the different combinations. So Q0 equals A prime B prime. Q1 is A prime B. A B prime for Q2, and AB for Q3. More commonly, you see 3 to 8 decoders, which just would have a third input and 8 outputs, Q0 through Q7. And there you go. Most commonly, though, you find that the outputs are inverted by the use of NAND gates. And so these are inverted like so, with a bar over everything. And the state table would be 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 1, 0, 1, and 1, 1, 1, 0. So you would have an active low output where the output is inverted from the output is inverted from the input values. So now there's one of the reasons why they do this with the NAND gates is number one, it's cheaper. It is less silicon on the chip, so because the number of transistors required for a NAND gate is less than for an AND gate. So, but also inputs, enable inputs for some devices are inverted, active low. For example, the tri-state buffer. It is non-inverting buffer, but it has a enable. Input. So the state table for a tri-state buffer is, doesn't matter what X is, if enable is high, Q is in a high Z state. 0, 1, L, L, 0, 1. So you have this device that if it's high, it acts like if there's no connection. I think I mentioned earlier in the semester that there are 3 states that a wire can have: connected to ground, connected to positive, and connected to nothing. That's what the high Z state is connected to nothing. It has no charge. It doesn't have a ground charge. It doesn't have a power charge. Whereas 0 and 1, 0 is connected to ground, 1 is connected to power. That is this is why it's devices like this that are the reason why that these are called state tables rather than truth tables. A truth table is either true or false. State table can have multiple states besides 0 and 1. So the tri-state buffer has 3 states: no connection, 1, or 0. Where that comes in handy is in the area of buses. If multiple devices have access to the bus, a bus like say a USB, which is a universal serial bus, you would want the devices not using the bus at any given time to have their access to it in a high impedance state, a non-connected state, so as to not interfere with the signals being used, signals generated by the device that is using the bus. I believe you get more into buses and bus contention and that sort of thing in computer org. It's a little bit beyond the scope of this class. But you have these decoders having active, what's called active low outputs. As you can see with the active low enable, the device is active when the input is low. So it is often shown with a bar over it to indicate that it is a active low input. So, but you can see how a decoder works. You can expand this to a number of different inputs. You can add an enable bit, a active low enable bit, and let's see here. And then if the enable is, that means it with the active enable, your uh, yeah, if your enable bit is high, none of your outputs are selected. It doesn't matter what A and B are. If you have an enable bit there, you can select which, using the enable bit, you can cascade multiple decoders together by having this common A and B bit, and then you have go to another decoder, and then have A and B here. From up here, and this is a 2x4 decoder. And when this is low, the output will be valid on the upper 4. When this is high, low and then high and then low again, it would enable this decoder and have one of these 4 be active. So by using enable bits, and these are all Q bar. So with enable bits, you can cascade the various decoders together to get more devices. The enable bit becoming the 3rd address in the addressable area. Let's see here. Now, let's see here. Now, you can also use this as a function generator, the decoders as a function generator. I'll go ahead and give you an example of that. So, say you have a 3 to 8 decoder. You have 2, 3, 4, 5, 6, 7, 8. And let's look at a full adder. A full adder is A, B, and Cn, right? And you have a sum and a carry. So you have 0, 1, or 0, 0, 1, or 0. Zero, 1, 0, 1, 0, 1. Okay, and your sum is 0, carry is 0. Let's see here. Sum 1, carry 0. 1, carry 0. 0, carry 1. 1, carry 0. 0, carry 1. 0, carry 1. 1, carry 1. Okay. So you have 8. You have A, B, and Cn. The sum is going to be, and you look at the Q's here, Q0, Q1, Q2, Q3, Q4, Q5, Q6, Q7. All right. Now, the sum and the carry is if the sum is going to be Q1, Q2, Q4, or Q7. So Q1, Q2, Q4, or Q7. The carry is going to be Q3, Q5, Q6, or Q7. Q0 is not used. But so you can use a decoder. This is a 3 to 8 decoder. active high outputs. Yeah. So you can use a decoder to generate functions of different types with different numbers of outputs with a little bit of extra logic and connecting them accordingly. So so there you go. Now, the inverse of a encoder is of a decoder is an encoder. Let's see here. You have, say, 4 inputs. Let's go ahead and get rid of this. Say you have 4 inputs, A, B, C, D, and 2 outputs, Q1 or Q0 and Q1. This is for an encoder. Assume only one is high at any given time. You want the Q0 and Q1 to be 0, 0 when A is high, 0, 1 when B is high, 1, 0, and 1, 1. Okay? So you have your, let's see here, A, B, C, D. Alright. Alright, so you would have yeah. Oh, those are your outputs. Those are the desired outputs. Q0 and Q1, or actually it should be reversed. Q1, Q0. The two-digit binary number that corresponds to the high input.
How do you know if it's 0 or how do you know if it's
Because this is in the 0 position, so it would be 0. Be the 1 position, 0, 1, 0, 1, 2 position, 2, 1, 0 for 2, and in the 3rd position, 1, 1, 1 or 3. So hmm. So here. So you would have oh yeah, oh that's right. Uh uh hmm. Been a while since I've done an encoder. I'm trying to remember. Oh, okay. So Q1 is going to be if C or D is high. So actually, you don't need these at all. You don't need the inverters. Like I said, it's been a while since I did this sort of thing, so my apologies. C Q0 should be when B or D is high. So B or D, Q0, and Q1 when C or D is high. Yeah, okay, it's easier than when I was what I was thinking in my head. But yeah, C is high when Q1 is high. I'm sorry, start from 0. Q0 is high when B is high, or D is high. So it's B or D. Q1 is high when C is high or D is high. So it's C or D. So you can take this out to be 8 bits or 16 bits and expand it with just simple OR gates. Looking at the what combination, you look at what combination indicates a high for that output. B and D for Q, 0. And C and D, C or D for Q1. Let's see here. For 3, so you have Q2 and Q3. You would have if you have now 3 outputs. Let's just do 3 outputs. Let's see here. And assuming you have D, E, F, G, and H, B and D, my glasses on, B, D, F, and H. And Q0 would be 2, 3, plus G and or H. And it'd be H, G, F, and E. If you had 8 inputs and 3 outputs, that's what the configuration, the OR gates would look like. Mm-hmm. Yes. Yeah, it would be if it would be 8, if it was 8 inputs, this would be twice as wide, and you would have one more Q here. You'd have Q2. That would be A through H. The book uses D0 through D7, but yeah. But that's how an encoder would work. So, All right, well, I will save multiplexers for next time. In the meantime, have a good day, have a good weekend. See you on Monday.